day everyone, or actually good night. Let me see if you can hear me. Yeah, actually the little chart which I have in Open Broadcast software says that you should be able to hear me, so good evening everyone. And apologies for starting the stream like so super late today. I basically just got back from work, so yeah. Okay, today's moderator is going to be Foxtrot Charlie, and you see his nickname right here. And apart from that, you might be seeing KrzaQ around as well, especially at the beginning of the live stream. So if you have any questions at any time, do ping either KrzaQ or Foxtrot Charlie, whomever you see. Or if you're on our Discord, I believe, or IRC, you can use the exclamation mark Q, then write your question, and that will get to me as well. So, yes, good evening, and today's topic is going to be reverse engineering virtual machine-based protections, part 2, which means part 1 was already last week. We basically went through a stack-based, like return-oriented programming-based shellcode, let's call it like a rope chain basically, which turned out to be an implementation of a virtual machine. So that means like we had one weird machine in the form of the rope chain, which was actually quite complicated. It had loops, it had switch cases and so on. And we found out that, hey, it's actually implemented another virtual machine. So we had like two weird machines, one being the rope chain and the other being the virtual machine implemented in the rope chain. And we will be focusing on the second part today. So yeah, before we get there, I guess a couple of announcements. As usual, one announcement would be there won't be a stream next week and probably neither in 2 weeks. And if you know Polish, tomorrow's stream is also off, and a stream in next week and in 2 weeks is also off. So yeah, we'll see each other basically in the second week of July, I believe. This might change, but that's basically the when I looked at my calendar, that was the case. So yeah, apologies for that. Apart from that, let's go through some usual stuff, which means, let's see, this is, oh yeah, it even shows the correct desktop. That's good, that's good. Would it show the browser? Here we go. This is KrzaQ's website. He's one of 2 moderators you might see today. So if you're interested, do check it out. It's dev.krzaQ. This is how you read this weird looking thing. I mean, if you're Polish, it's not really weird looking. If you are not Polish, it is weird looking. And you read it KrzaQ, so yeah, do check it out, dev.krzaQ.cc. And then this is the website of my second moderator, Foxtrot Charlie actually, and the website is foxtrotlabs.cc. So check it out as well. Now, I actually opened my Twitter account because of a couple of reasons. One reason is that Ricardo, who I commissioned to do another paged out cover, basically finished his work. I basically, like, we hired multiple artists to do the covers, so we have like several covers ready for the upcoming issues. After we've completed the first one, I kind of expect that it will be a little faster with the next issues, therefore I wanted to have the covers ready. So yeah, this is one of them. This actually was, this is a pixel art, and there are 3 versions of this. This one is like more on the pinkish side, but if you look in the thread, there's also like one which doesn't have the bloom effects, and I really like it. Like, this is a really, really nice pixel art. It's really well done. I just really love this car here. It looks just amazing. How can I get rid of, yeah, let's do it like this, yeah. This car here, I really like it. I mean, it's just perfect. So yeah, there you have it, another cover of Paged Out. And speaking of Paged Out, we are still missing, I believe, so it shows 33. I think we have one more actually article in the queue, so that would be 34. 16 slots still left. Well, at least we need at least 16 articles to get here, which means that if you want your article to be in the first issue, then yeah, you'd have to send it in, I guess, in the next couple of weeks. I'm pretty sure we should be able to have the issue ready by the end of July. And the articles are really cool, actually. So yeah, I'm really looking forward to finishing it up. And then we'll be collecting articles for the second issue, which should appear in around 3-4 months as well. So that's one thing. The other thing is, yeah. So actually, this is kind of related to page layout as well. If we go back to to this page, you know that Reverse basically published another article, an example article, and there was a challenge. Well, actually, like a fork of a challenge in 2 versions was published. A CTF challenge, reverse engineering challenge, rather on the simple side, but not trivial. Yeah, and there was, let's say, a competition to solve it. Or is it still going on? I'm not really sure. Maybe no. Anyway, Reverse did one amazing thing. He basically chatted with a couple of really like well-known YouTube security streamers or like Twitch security streamers, and they recorded how each of them solved it, and like it basically became like a reverse engineering race. To steal the pony race terminology, it was like basically a how to solve a reverse engineering challenge race, and this was published on his channel. So yeah, as you can see, like he convinced Murmus, CTF, Zanit, you might know his channel, it's DevNull with the slashes, John Ammont, and Live Overflow. So yeah, go and check it out. It's really amazing to see like these 4 people going well head to head basically, and also the commentary which Reverse provided is like spot on. So he also does like zooming of important things and like pointing out what is going on, so it's not like chaotic, but really well done. And you can see like how these people think and how they approach the same problem from different angles. I really recommend looking, like checking it out. I guess I'm going to give you a link to it as well. So yeah, thank you for making it. It was like I'm really happy that this was made, and a lot of effort was put into it as well. So that's the second thing or third thing I wanted to tell you. The last thing is called a Google CTF, or like JCO CTF. Let's just go here. Yes, Google Capture the Flag is starting this, well, depending on what time zone you're in, it's either going to be this Friday for you or it's going to be this Saturday, really early in the morning for you. I guess for us, like for my time zone, it's going to be really early in the morning on Saturday. And so yeah, the whole Saturday, whole Sunday, basically, there will be the qualification round of Google Capture the Flag. And there will be some amazing challenges. I do know that because I did participate in either making or testing the challenges. And there also will be a beginner's quest track, like multiple challenges for beginners with some story around it as last year. So I hope you enjoy it. It's going to be fun. I'm really hyped for it. And you will be seeing me on the IRC of Google CTF as well. I will be probably during nights helping out a little. Cool. So yeah, capture the flag with google.com. And I think if you go to like CTF time, it's like 100 points or something worth. So yeah, rating weight 96. So this is like a super high weight CTF as well. And if like 10 best teams qualify and they go to the on-site finals somewhere around, I think October, November, should be fun as well. Cool. So I'm going to take a quick look if there are any questions from you folks, and do my questions actually work? Will they be displayed? And if not, we can get to overall questions. Is there a digger on your ship? No, it's like a moon buggy basically, or a Mars buggy. It was created by basically like a university team from one of the Polish universities. I believe it was from Częstochowa, I think. And yeah, the folks were basically, doing like a crowdfunding to go to like NASA championships or something related to that. And I also threw in some cash, and I got a cool t-shirt. And I also got a cool photo from the folks. So that's it basically. Which assembly book can you recommend beginner intermediate? That's a good question. I cannot recommend anything, not because there isn't anything good, because that's probably not the case. It's because I haven't looked at any assembly books recently. Well, at least x86 assembly books recently. So, I don't know. I mean, the Intel Manual Volume 1 has a lot of basic information, but that's not a book to read. It's like a reference manual. So it's a good question. I would look at wiki books if there's something assembly related. Apart from that, I mean, in all honesty, it doesn't really matter, because from my perspective, and I'm sorry, I know I'm sidestepping the question. From my perspective, it's like this. When you are learning something like assembly, you basically need like 5 different tutorials, 3 different books, and like 2 reference manuals, and 10 different pieces of code from other people, and 20 tutorials, and you jump between them while trying to write your own assembly code or read some assembly code, right? So yeah, I guess like also recommending just one book isn't the way to go. But yeah, that still goes to the beginning with me saying that I have no idea what books are available on the market right now. Sorry. Unrelated question. I have a secure exception, not secure, structured exception handling overflow with Win7 protections. I'm trying to pivot from the sec handler. No add ESP gadgets, no control register. Any tips? Not really. It's like it's been a long time since I have been looking at it, and I don't know what the usual ways were to do that, especially with Win7 protections. I was playing with that and exploiting it on WinXP, but then it wasn't protected. It was quite funny actually, because like you just overwritten the stack, overwritten the return pointer, and yeah. I mean, it's quite weird that by the way, do you want add ESP gadgets or do you want sub ESP gadgets? Yeah, I don't know. I'd have to look at the specific case. I would basically look in the direction of finding some weird gadgets which might work, or looking what's exactly on the stack which can be used in combination with some weird gadgets, because you could override the basically the exception handler pointer on the stack, and then to go to some weird gadget, and then that gadget would use something from the stack which would return to the stack in a different location. But also depends if you actually know where the stack location is. In the end, it is case specific, so I would deal with it in a case specific basis. So yeah, sorry. No good generic tips from me. StreamPal, Foxbridge. Okay, I guess we are testing Foxbridge. That's cool. Perfect. So I guess we can go back to trying to solve the challenge, because that's the ultimate goal for us. Again, we finished last time basically looking at the at this. Yeah, this is what we are looking at. And this is the disassembled part, especially if you look at this, at this column here. This is the bytecode of the ROP weird machine, and we figured out that this is writing something to memory. We know that these are like the second layer of the second virtual machine bytecode, and these are written somewhere in memory. And then we later found that there is a large loop with a switch case, and the switch case, this is the switch case basically for each of the for each of these instructions. We basically this is this the switch case? Yeah, it is the switch case. Here, for each of these bytecodes, and we know this is the bytecode. We jump somewhere, and that somewhere is somewhere lower, where each of the machine code or bytecode of the layer 2 VM is implemented. So basically what we have to do now is we have to analyze what each of these opcodes actually does. So what is, for example, like FFFF, what is like 1010101, what is like B00001, B000F, what is like 1337, 1337, and so on. We need to analyze what this is. We need to also kind of, I guess, execute this to get this somewhere in memory, then dump it, and write another disassembler based on what we know to get code like this. Because I don't want to do anything more with this code here, because there isn't really much need for it. What you could do is you could, for example, try to put this in a graph form. For that, you would use the dot library, where you basically just write in a text format the edges, the nodes, and well, the edges would be just, you know, jumps from one node to the other, or other connections. Like, for example, there's a stack pivot is a jump here, basically. So yeah. So these would be the jumps, and you could have a nice graph view. Here, I don't think it's really needed, because there is this one huge switch case, and that's basically it. And the switch case is in a loop, so yeah, we can basically figure out how it looks like, and I can just draw it for you. It's like initializations at the beginning, which is writing stuff into memory. Then we have this switch case, which basically branches out into multiple potential like bytecode implementations, and they probably all of them either just jump to some common node that doesn't really matter, or like, let's say it's a virtual node, and that virtual node basically just goes to the beginning of the switch case, because this is a loop. It basically like increments the instructions and goes to the beginning of a loop. So this is the graph which we would get, and I don't see a reason, in all honesty, to write code to write that graph. Which means we do have to probably analyze it. Not this code, because this we already know, but what does each of these do. But before we get there, I would really like to get this stuff written down in memory. And if you look how it works, and that's again something we decided on yesterday, like this address, basically in EDX you always have the address, and you write whatever is in the ECX register. So this here. So this is basically put here, the address is basically put here, and is going to be like ECX value is going to be stored there. And then the address is increased each time by 4 bytes, 4 bytes, 4 bytes, and so on and so forth. Yeah. So yeah, I would like to dump this, and once we have this dumped, then whatever. And to dump it, what we have to do is we basically have to, well, go to the end of it. Where is the end of it? Here. Okay, so this is the last store, and this is a gadget which puts some value in EAX, and the gadget is like on this location, and this is the address of the code of this gadget. Let me maybe make this a little bit bigger, and let me maybe open IDA again. Do we have a link to the challenge in the description? If no, Foxtrot, if you have a moment, if you could find the link to the challenge and put it in the description of the video, that might be helpful. Yeah. So what I want to do is I want to go here, like just jump here, jump to this address, here we go. And this is some weird unwind thing, which probably is never used in the application. Unwind is basically like used for exception handling in C++. So what I will do is I will basically set a breakpoint here, because it will get executed once the execution goes here, and at this point I know that all these instructions have been already executed and the stuff is in memory, so I can just grab it from memory, dump it to a file, and yeah, and like look at it from, I don't know, Hexedit or whatever I want to do with it. Okay, but to run it, I do need to get a Linux console, basically. What kind of file? Okay, it's 32 bits. Okay, that should be fine. So just another matryoshka, and as mentioned, I do want to this address. I want to do a break on this address, so break and asterisk and the address with OX obviously. And now I'm just going to run it. I think I am supposed to put... I don't remember what was the input. Let's go to main and see what's the input. Blah blah blah. Scan up to 32 bits and then verify the passwords. Okay, so it doesn't matter. I'm just going to run it with ASDF. And oh, it doesn't take it as the argument. Scan saves it. Okay, and then it stopped here, which means that all this has, the storage has already finished. And what I need now is basically to just dump it from memory, just read it from memory. I can do it in a couple of ways. One way is I can just use, GDB. Another way is I can actually go to the process memory, but I will do it with GDB. Just let me note down the addresses. So I've created this notes document, and this is the last address. Sorry, this is the last address where things are going to be stored. So I'm going to add 4 to it. So C is the ending address basically, and the first address where we store stuff is here. So okay, now I never remember how to dump stuff in GDB, so I'm just going to look for it. If I find my browser, I'm not sure if I'm going to find my browser. Well, here we are. GDB dump memory. Dumping memory. Yeah. No, I want to dump it to file. GDB dump memory to file. Where's a command for it? I don't know. Yeah, dump binary, this is it. So dump binary memory and the addresses. Yeah, I'm pretty sure these are the addresses. So I think memory is actually the name of the file. Missing stop address is not the name of the file. Help dump memory. Okay, so file arguments are file, so here we go with the file name, like dump L2 as in level 2. Invalid memory start is bigger than end. What? Wait, what? No. So this is... yeah, it is bigger than end. Why is it bigger? AB, do... maybe there are like 2 regions of memory. So it's still like AB 50, 60, 70. Maybe I copy pasted the wrong address. Still AB. Maybe, oops. Yeah, I probably copy pasted the wrong address. So here's the end, and I copy pasted this. Oh, okay. Oh, that's actually interesting. So this is the last address. But it's a happy accident, how like Bill Ross called it. It's a happy accident because we just learned that there are 2 segments of memory. And furthermore, because there isn't a lot of stuff here and almost everything is written with zeros, my bet is that this is going to be the instruction pointer address and these are going to be registers. And I don't remember that it was like this. This is just my bet because there aren't too many stores here. There are like 8 stores here around. So, and a virtual machine is either a stack-based virtual machine or it is based on registers. It could be both, but usually it's like this, right? Which means that somewhere in memory the register values needs to be stored. And that's true for virtual machines, not for like real CPUs, of course, because these are stored in like special, really fast memory inside the CPU anyway. Which means that due to these addresses being disclosed to us, we have and like the number of them, I'm pretty certain these are going to be registers. Which is actually super cool, and this is super useful to know. So it's good that we got that error, and good that we noticed it, because it is going to be useful. Yeah, I think it's Bill Ross, right? I'm sorry if no, it's not Bill Ross. I'm so sorry. Bob Ross, not Bill Ross. I apologize to everyone for that mistake. That should not have happened. Okay, so I need to change, wait, that was good. Dump 1 and the address. Yeah. Okay, now we have it dumped. It's not a lot, it seems, so let me just quit GDB. It's just like 600 bytes. So if we open it in a hex editor, which I'm going to do, and my hex editor has this funny little function where we actually do, wait, that's not the function, this is the function. We can actually do something like this. So yeah, this I'm basically just displaying, 4 bytes at a time. And we can take a look. There are a lot of these, whatever these do. And I'm wondering, because I'm split between two theories or like hypotheses. One is like that each opcode is 32 bits, and an opcode can actually have, like a bytecode could have 1 argument, or could have 2 arguments, or could have 0 arguments, or it always has 1 argument. And if it always has 1 argument, it makes more sense to actually show it like this. But as I guess as we can see here, this is like pretty random. But here, yeah, I'm pretty sure that's not the case. I'm pretty sure it's actually like just variable length instructions, 32 bits, 64 bits, or like more. And there's not a lot of it. I guess like we have like dead. This is what it would say, hexadecimal, right? Dead. So dead, I'm pretty sure it's just going to be exit. We can check, we can basically start with that. Let's go to implementation of dead. And so where is the implementation of dead? Oh yeah, here it is. Dead, and this is a comparison, and if something, then jump to this address, edx. This is the address where it's implemented, and this is like actually a stack pivot, so jump with esp there. So I'm going to go there. No wait, there's an offset of 4, but which direction was it? Was it this direction? No, it was latter, this direction. Okay, here we go. And this is, I guess, the code, which ends here with this jump. This jump, if I understand correctly, is, yeah, so, no, it was 8. Where does it jump? What kind of jump is this? It's not a stack jump, right? I was thinking it's a stack jump, again, like a stack pivot. But no, it's an pop ESP. No, it is a stack pivot. It is a jump. Why doesn't it just show it to me? Where does it jump? That's pretty weird. Well, okay. Wait, one more thing. Did I misread the address? F6, no, that's fine. I was thinking like all these jumps are always to the same location, but maybe they are to a different location. Okay, let's see what's going on here. In that case, we basically read from this address +4, and we put it in EAX. Then we get this address, and we put it in EDX. Then we do EDX equals this, and we do another store. So these are like 3 stores. What are these addresses? I'm not really sure what are these addresses. Yeah. Why are we storing something here, and then we are jumping to a weird location? Why is this weird location like this? Is this... Why? Yeah, this is SMC. Like some kind of SMC or JIT is like creating new code in memory and jumping there. I am not happy about this, in all honesty, because that means it's I hope it's just like putting a return value and doing a jump. I hope sincerely that's it. It might be something weirder. So we jump here, which means that this is going to be loaded. This is probably one of the registers. So I'm going to oh, I see we have like noted from the last time, but it's probably exit anyway. So now we have like another, we think for another reason it's an exit. So this I think is one of the registers. We load it to EAX, and then what do we do with the EAX? No, we just load it to EAX and we store it somewhere here. And then we put here is probably on the stack somewhere. We put this and ECX. This is going to be, we want to check what is under this address, and this address is probably somewhere in the code, as in this is actually a gadget. So if we go here, oh yeah, it is just an exit. So that's why we thought it's, okay, so it's just calling exit. And we, I guess, figured it out last time anyway. So yeah, so we know that dead means it's actually just an exit. Or exit like EAX actually. Which is quite funny because I was looking for a return and I found an exit, which means that coming here isn't great. I don't want to arrive here, and I probably don't want to arrive here. I don't want to arrive at the deads. So nor here, neither here. Then what happens if I actually type, like if I get the wrong password? Let's just run it. ASDF. It says verifying password. Nope, sorry, wrong password. So I'm wondering if this nope, sorry, wrong password wouldn't be written out by some of these things. Like 777 or 666 might be a puts. Let's try to verify that. And to verify that, we have to again go, so this is, yeah, let's just make it like this. I'm not sure really what's happening here, but whatever. Okay, and now we need to look for the 6666. So 66666. It's writing to memory, but we are looking for the switch case. That was it. Previous, perfect. In this case, we are jumping here, so I'm adding this. And yeah, and here we are. So where's the nearest jump? The nearest jump is here. Okay. So what does this do? It loads some stuff. It stores some stuff. What I'm more interested in is where is it jumping to? It jumps to somewhere, which is all the same address, which is probably the beginning of a loop. And does it do anything other than that, or is it just like filling a buffer? It's quite a lot of instructions to actually implement something. You know what I'm going to do? I'm going to like mark that this is 66666666, and I'm going to go back. Okay, here, and I'm actually going to note the addresses of, oh, I have them noted actually, like these addresses. Because these are, we know these are registers, but we need to find out what kind of registers are these. So that would be 88, ATC, 90, 94, 98, 90C, and A0, A4, and at the end A8. I think A8, is it still a register? Yeah, it is still a register. Perfect. So these are the VM registers. And it's quite easy to find out which one of these is the program counter, which one is the instruction pointer, points to the next instruction, because we just should be able to grab it from somewhere here, because, yeah. So this looks like it actually. Like 80 plus 4, that would be 84. And we grab the value from there, and the value there is going to be the instruction pointer, right? So we get the value of the instruction pointer, and then we load the instruction from that address. And once we have loaded the instruction from that address, we do the comparison, right? This is where the comparison is going on, or is it going on somewhere else. We are doing this ESI, ESI, and ESI is set to EAX. Yeah. So yeah, I'm pretty sure that this is the instruction pointer. Or PC, like program counter, however you want to call it, right? It's the same thing, basically. So these, my bet is that these are general purpose registers. I guess we can set what are, like, see what are the initial values of all of them. For example, let's see what's the initial value of 88. Did I scroll too far? Yeah, 88 is here, and we put a 0 in the 88. So this is initialized to 0. Then 80C is also 0. 90 is actually also initialized to 0. So is 94, it's also 0. 98 is actually initialized to this value, which is, we need to figure out, yeah, what is this value? It's a real value. What's in the, sorry, that's not IDA. What's there? Oh, it's the password field. How interesting, isn't it? And it's exactly this, yeah, so this is like pointer to password, to user input. This was lucky. Then we have another address, which is put to, wait, what about like everything in the middle? There's nothing here, nothing here, nothing here. And then suddenly in A8 it puts like some value. So these might be like separate set of registers. It might be like only 4 registers in this virtual machine. I don't know, maybe. So let's go in IDA to this, like G, jump here. No, it's some free space. Where are we using this free space anyway? Is this stack? It's probably not stack because it wouldn't be in IDA, so yeah. I'm not sure what this is. It might be just some free memory region, for all I know. Yeah, I don't know. It seriously might be just a free memory region for the application to use as the application, like the, you know, the layer 2 application wishes. So okay, we know this, and we can, thanks to knowing the registers, let's just call these, like, I'm pretty sure these are like general purpose registers. So this is going to be R0, this is going to be R1, this is going to be R2, and this is going to be R3. Therefore, if we want to figure out the 666, we know that there are opcodes like 666, 777, I also saw like 1337, 1337, and several more, but we will get to them later. I wanted to analyze the 666 part, and the 666 is here, perfect. So, here, we grab, yeah, it's the 80 plus 4, so this is grabbing, EBX is not important here, well, whatever. The important thing here is that in EAX now we have the instruction pointer of the virtual machine, right? Then in EDX we store in EDX the value, EDX being this A0, this is this, right? It is this, so I don't know. It's not initialized, but is obviously being used. And here we store this value which we got from EAX. So, okay, so this might be, actually it might be like this. This might be R4, R5, R6, and R7. It might be like this, but there's 8 general purpose registers, which is pretty possible because everyone, you know, likes nice round numbers as in actually powers of 2. Okay, so here we store in, you know what, I probably should like do this. No. Trying to find like a proper Windows setup so I can see both without jumping between them. Okay, should be fine now. Yeah, cool. So here we actually this doesn't matter. EAX is IP, and here in R6 we store the IP. So into R6 we put IP. This is like 1. I'm basically reverse engineering this stuff. Then in 80 again we load the instruction pointer to AX. So oh no, this is wrong. This is not IP, this is what was under the IP. So like IP, dereferenced. Then in EAX we put, so in EAX we have the IP again. Then we do minus this. This is basically adding 4 to, yeah, because this is like minus 4, right? So it's adding 4 to EAX, which means we have EAX plus 4, which is cool because it's reading the argument probably. So we know that the 666 thing has like one arc. Well, at least one arc, maybe more arguments. We'll figure it out soon. And it's putting it, it's putting the EAX, the value which it figured out, in EDX. So now in EDX we have IP plus 1 and this referenced. Or is it the address? No, it's just the address of that. So it's IP plus 1 or plus 4, whatever. Depending if you want to count the D-words or count the bytes. Let's say we're going to count the bytes. And we put it, no, we don't put it in EDX, we put it in 84. What is 84? 84 for us is the instruction pointer. It's a jump. Well, what? Weird. So what's the instruction pointer where we put? No, this means this sequence here is actually just incrementing IP by 4. So yeah, it got the address of IP, then it incremented it by 4. Which I'm guessing we are going to see this a lot, this pattern, right? Yeah, this pattern, these exactly 5 instructions. Then in EAX we put A4, which is R7, but plus 8. So yeah, this is this weird thing here. So we get this weird thing, I don't know, what is this? Let's say it's the stack pointer. Let's assume it's the stack pointer. I'm going to assume it's the stack pointer, I might be completely off. We get the stack pointer address here, and we load the address, so we get and we load what is under that address. Does that make any sense? Not really sure. Actually, no, let's say B. Alright, I don't know. I'm going to assume it's a stack pointer, maybe I will be corrected. So in EAX now we have whatever was in the stack pointer. Then 9C. 9C is R5. In R5 we store whatever was. So R5, whatever was under the stack pointer, or whatever pointer that is. Then EAX is A4, and we load into EAX that again. So we load the stack pointer thingy again, because that's A8, because plus 4, right? And we put it in EAX, so we have the stack pointer there. And then ECX is 4, we decrement that by 4, and we put it back here. So yeah, basically that means that the stack pointer is decremented by 4 minus equal 4, which means this totally looks to me like a pop, right? We read something from the stack, but then we decrement it instead of increment it, which is weird. But are we actually popping from the stack? We are loading, we are saying, no, we are pushing. This is a push. So this is pushing something on the stack. What are we pushing on the stack? We are pushing EAX. What was EAX? EAX is taken from here. what was in EAX here? So A4. That's weird. Yeah, it kind of looks like a push. Yeah, so I don't need this. EDX is this. No, it is a pop. We pop a value to R8 register. Because yeah, we read the value, we pop the value to R8 and then we move the stack by 4. So this is a pop. And then we jump to the beginning, I guess, of the instruction. Where is this? No, it's the end of, or is it the beginning? We jump, I guess, here, somewhere here, or maybe here. Yeah, it's the beginning of the loop. Okay. So what is this going to do? I think I'm missing the purpose of this. I understand that we are popping a value, but apart from popping the value, this is quite interesting. No, it's not interesting. It's actually like we are just incrementing. Yeah, we are moving to the next instruction, and so this looks like just like a pop, basically, like pop R8. This is what I think this instruction is. Like a lot of code, there is no argument, it's just like going to the next instruction. Pop R8, this is what I think it is. I might be wrong, I think that's what it is. So this is not needed. Why do we put something in R6 though? Why do we put the IP there? Because it's maybe it's a temporary value for some reason. EDXA, yeah, this is R6, we store it there. I don't know why we store it there. Then we take this, we load from, so 84, we load from 84 again. So we load the IP, we decrement whatever we had in AAX, so we decrement the IP, and then we store it under EDX, where the EDX is going to be the IP. So yeah, this is obvious, this is not obvious, this is obvious, and this is obvious. So it's a pop R8 with a twist, with like R6 getting the IP. It might be totally wrong. I'm like, that's not R8, there is no R8. Why do I say it's R8? 9C is R5. Yeah. It might be totally wrong for like I think I got it right, but if I got it wrong, then it's going to be either a return or it might be a return. So like pop and jump or something, got a call. Oh, I see you. Blame drop and Pavel also spotted my back in the like with R4, sorry, R8 and R5. So thank you for spotting that. So okay, so this is some kind of a pop. It's weird. I'm not really sure. Then we have zeros. I have no idea what zeros are. Do we have even an opcode which is just zeros? So let's just jump here. You know what? I'm probably going to remove the top of the code. Because we already dumped it, so we don't really need it. And we already written down the initial values, so we don't really need it either. I'm going to remove this just for simplicity. Okay, this is store, and this is where the fun begins, right? Yeah. So this is 1, this is 2, for each stack pivot. Okay. And we did decode this last time, and it was like some, yes. Sorry, goodbye, go away. Okay, so let's look at the opcodes. We have this opcode. I guess I can like note them down, the ones which I don't have. I have that, I don't have feed data. Like just reading this ASCII opcodes is interesting. Feed data, what does it mean? Is it like a poke, a peak? Okay, 333, no, like sorry, C, which I said 333 because it reminds me of interrupt 3, which you know on x86 CC is int3. Just random things you have in your memory. 90, 90, 90, 90. Hey, wanna bet that is going to be a no-op? Like no operation, do nothing? Okay, then. Well, that's funny. Like 1, 2, 3, 4, 5, 6, and then my like shifted by 1. Then we have 1. Okay. So 1. Wow, I actually thought this was going to be like this is going to be some parameter, but obviously it's not. Okay, then we have f's. I do not have f's noted either. Then we have 1s which are misaligned. So 0. Quite a lot of opcodes actually. As counting is going to be less, but yeah. Anyway, I'm not too worried about getting this proper and properly reversed right away, because I'm pretty sure I'm going to learn a lot of more patterns on the way, and I can always revisit it. Then zeros, and then 1, 3, 3, and then bad, bad, bad. Okay. 7, 7, 7 we have here, 6, 6, 6 we have there. Then, yeah, and then there's some other stuff which is not important, which is not related. So these are the opcodes which we need to reverse engineer. The question is from... I can show you the questions. KrzaQ. I hope that is how you read your nickname, KrzaQ. If not, let me know. Did anyone solve it? Yes, actually yes, several people solved it. What do you recommend for beginners to learn and start a career in cybersecurity and CTF competitions? These are kind of like separate things, right? CTFs and cybersecurity. I guess like, well, depending on like cybersecurity is a huge thing, right? And depending on which way do you want to go on more like application security, network security, infrastructure security, forensics, or like whatever else, right? If you want to start like with bug hunting and like security research, basically, then CTFs is a good idea to start with. And I guess like start with web security, because web security is easier, and then you can go to low-level security, which requires learning like some assembly, some reverse engineering, knowing really well how everything works. Web security is slightly easier. It's not a lot easier, but it's slightly easier. So web application security, both on the client side, like XSSs, XSRFs, and both on the server side, especially PHP. PHP is a good target to start with, because there are a lot of vulnerable applications which you can play with. So yeah, I guess I would go that way. And if you're thinking about starting with CTFs, find a team or create a team and read a lot of write-ups for CTF challenges. Yeah, you don't even have to solve the challenges yourself, but read the write-ups, so you know, you have some knowledge or where to find something basically in your head. And then just do challenges, play CTFs, and yeah, I guess the questions have to start, so there we go. What about doing the whole Google Beginner's Quest with no preparations, multiple episodes, unless you've already seen solutions, help with the tasks? Yeah, that might not work. I'm probably going to, after this weekend, I'm probably going to know all the challenges in the Beginner's Quest track, so yeah, that's not going to work. I don't think I'll have the opportunity to not know them. But I actually want to play with them anyway, so yeah. You can make columns between 2 files in Sublime. Yeah, I know. But I want to keep this like, you know, above my camera, like this camera border here, right? I want to keep this window higher without having to scroll up. Yeah. But I know, like, what, Control Alt 2 or something. Perfect. So, okay. I told you that this is going to be a no-op. Let's take a look. How wrong was I? Here, when we jump, blah blah blah, we jump. Where do we jump? We do a pivot to EDX, which is this, which white. What? Oh, we compare them. Oh, something's wrong here. Why is it here? Something is displayed incorrectly. Oh, whatever. Is this the address where we jump to? So that would be AO, I believe. Yeah. Surprise! We found just a jump with no other stuff here. No surprise, no surprise. Nobody is surprised. This is a no operation. As the Intel manual says, it performs no operations on the CPU or universal. So fnope, which performs no operations on the floating point unit. And we jump. Where do we jump? We jump. Okay, a lot of jumps there. This is the jump to the beginning of the loop. Oh, that's weird. What is this code? Okay, but yeah, this is the beginning of the loop, so that's fine. So this is an op. Now let's look at C. This is jumping here. Oh, I know what this is. This is the address of the next instruction. This is fine. It's displaying fine. No, I was mistaken. So we look for this address, and we don't find it. EDX and swap. Why do we not find this address? No, we find it. It's here. And this is, surprise, surprise, is a breakpoint. Anyone surprised? No? Okay. And 3, breakpoint, and then return. This might be useful when we will be debugging the application, basically. To know that this is a breakpoint, because you can overwrite any stuff here with like CCCCC, and then it will just break there. So it was probably used by the creator of this challenge to debug stuff. Cool. Then anything else looks really suspicious? I don't know about this, like... Oh. This looks pretty suspicious to me. Just please look from the beginning of the file, not from the end. Oh, wait, it's just 0, right? 0x0. Come on. Okay, so it's here. And we have to jump here. Okay, so we jump here basically, and it ends here. So this is rather... Yeah, I'm not sure about this pop right now. It might have been a push after all. We'll revisit it. Because like the NOP instruction didn't have any increment of the IP. And that means that if the NOP instruction didn't increment the IP, then the IP incrementation is done somewhere else. And that's probably on the top of the code. And if that's done somewhere else, then that means that the pop actually did use an argument. And if it used an argument, it might not be a pop. We will have to get back to that. What do we have here? This is 0x0000. Yeah. Like, is this 8? That's 7, 8. Perfect. And what do we do here? We store ECX, which is this, into A4, and A4 being R7. And we store this into R7. Why? What's on this address? What kind of address is this? 10. It's... I don't know. It's like some address here, actually. Here we do a jump. So it's something which is in between here. And we... What do we put there? We put there this. So it's 816BO A4 6B O A4 6. No, it's not this range. Yeah, I'm not really sure, but it's somewhere here, this address. I wonder why we it's not displayed here. Did I remove it by accident? Or did I like not display it by accident? But okay, for some reason we put I don't know what it does actually. Like, no idea. So in R7 we put this value? Weird. I don't know. It might become clear later on actually. Now let's look at FFFFF, for example. The order doesn't really matter. We go to here, so let's just jump there. And it's going to be this address. So this is FFFFF. No. Okay, and the F's itself, what is going on here? We take this address, which is 84 instruction pointer plus 4, so that's R0. So this is loading from R0. So EAX is R0. Is that correct? Yes, that's correct. ECX is 1. EAX is minus, so that's like here we have it's actually like R0 minus 1. And then to this address we store, okay, so this is easy. This is basically just like decrement R0. Or like R0 minus 1, whatever you want to call it. And yeah, I guess like we should have figured like FFFFF, but even sounds like this, like decrementation. So my guess is going to be that this one is going to be incrementing R0. So this is like dec R0. Yeah, seriously, my guess, but it's going to be jumping somewhere here and it's going to be okay, yeah, it's here. Let's just go here. 9 C. So it jumps here, no surprise. And we have 9 characters, it's wrong. Let's see, we're loading R0, we're putting this and decrementing, yeah, this is increment. No surprise, as expected, basically this is the reverse. So this is increment R0. We have something. So yeah, we are now reverse engineering. We already, like last episode, we reverse engineered the first layer of a VM, and now we are reverse engineering the second VM, which is implemented by the first layer. This is why this code looks really weird and doesn't look like x86 assembly, because this is what we generated by our disassembler in the first episode. So this is starting to make sense, but like, well, some of these are starting to make sense, this isn't. What is... Okay, so if 666 is going to be a pop, then this might be a push, and we might want to analyze them together. Before we get there, let's go with like 01, 01, 01, 01. What are you? There are only 2 instances of it, and we need to jump here basically, so let's just jump, come on, 8, and that's probably here. Why is there something missing here? I don't know why there's some... Oh, right, it's missing because it's probably displaying the address of the second operand instead of the first one. That's fine. I can live with that. Okay, and this is way more... Well, okay. I don't know where the jump is yet. Where's the jump? It's here. So it's not way more code. It's just this. Sorry for panicking. Let's see. 84. This is loading R0. So here in EAX we have R0. Then we put in ECX 0 and we subtract 0 from EAX. Why do we subtract 0? We subtract 0 because we are looking at the flags. Yeah. So we are looking at the 0 flag, and the 0 flag is going to be only if R0 is 0. So this is basically checking whether is R0 equal to 0. So it's basically like test R0, R0 if you speak x86. And if it is, and if it's not, what's happening here? We either jump to D8 8. We might jump to here, or otherwise we jump to BC, which is here. So yeah, this is one place, and this is actually the okay, and it looks like it puts either 1 or 0. It stores 1 or 0, like 1 or 0, and this register, which is R1. So this means that this is basically R1 is going to be equal to R0 equals 0, and just let me make sure I get the flags correctly. EDX is what's going to happen if 0 flag is set. So if R0 is 0, then EDX is set. So we have this BC here thing. BC is, where do we jump with BC? We jump here. And we set 1. So yeah, this is basically this. So R1 is going to be 1 if R0 is 0 or is... So yeah, that's a really simple check, really low-level check. You can find these kind of checks on like 8-bit CPUs easily. We don't know if it's an 8-bit CPU. It actually looks like the registers are 32 bits, so yeah. Okay, let's look at B001 and B000F. These also seem to be related, and we basically like end here. Let's just note it. Okay, and we need to jump to this address, like, yeah, 20, this is the end. So here we begin. Okay, where does it end? That's the question number 1. It always ends with a jump, right, to this address. So it ends here. But I see there's also like a jumping again somewhere here, so we are probably going to 54, 84, so we are jumping here, and yeah. So this is where the end is, actually. And since we do a pivot, yeah. So this is like, again, it's a function like do something and then go either this direction or this direction. What are we doing here? We are getting 88 plus 4, so 80C, that would be R1. So we are getting R1, then we are subtracting from R1 minus 1, we are subtracting whatever is in the ECX, and then we compare if it's 0. So it's basically comparing R1 to 1. Yeah, so is R1 equal to 1? Do I read it? Yeah, it's this plus 4, that is R1, that is not R0, it is R1. And if it is, then if it is 0, so if they were equal, as in like R1 was equal to 1, we go to EDX, EDX being 54, which is this branch. In this case, if R1, I should start noting this, B1 here, is like if R1 is equal to 1, then we go to 80 and 84, which is the instruction pointer. So we load the instruction pointer, we load whatever the instruction pointer is pointing at, and my guess this is the argument, by the way. So we will have to fix this thing. My guess is now that it's the argument. EBX doesn't matter. So EAX now holds the argument of this opcode. So that would be like if we find the B001 this here, this would be the argument. Okay, and then EDX hold this value, 84. 84 is the instruction pointer. So we store this value in the instruction pointer, we store the argument in the instruction pointer. So this is a jump, this is a conditional jump. So IP is equal to like arg, yeah, like this. Otherwise, if that's not the case, my guess is we are going to increment EIP by 4. That's my guess. Let's see. We read the EIP, we put minus 4 into ECX, this is minus 4, and we do minus 4, so plus 4, we increment it by 4 and we store it. Yeah, this is a conditional jump. So conditional jump if R1 is equal to 1. Go to arc. Then, okay, my guess, this is going to be really similar to this, but it's going to be a different kind of conditional jump, but it's still going to be a conditional jump. It's going to, for example, check 0. So let's go here when we need to jump here, and we are here. Okay, now I think I was wrong. So because it's way too short to be another conditional jump. I can't have all my predictions correct, can I? We do load. So here we have the argument. So EAX is the argument. Then we get the instruction pointer. This is an unconditional jump. Yeah, as you can see, I kind of like started recognizing the patterns which I see. When I see these patterns, I know is loading the thing which is IP is pointing at. When I see like this pattern, I know it's storing the IP. So it's going faster and faster with each instruction. So this is an unconditional jump. Just go to whatever the argument is. How many of these do we have? So we have... do we have any? Let's look for hex values. It's little endian, so it's OF, OO, OO, OB. We don't? Yeah. We just have like... Oh no, it's B0, yeah, like this, okay, sorry. So B8, BF, oh my. What happened? Yeah, we have at least one. Okay, so there's probably a loop, a conditional with unconditional loop. It's going to be a for loop. We know it's probably a for loop. Last week we found also the XOR instruction somewhere there. My take is that this VM, this bytecode which we see here, is going to XOR whatever we input and compare it with something. That's my guess. I'm not sure yet, but that's my guess. So, what are we missing then? We are missing bad. Let's look what bad is. This is going to be this, so let's jump here. Let's jump here. This is okay. Now, where is the nearest? Where's the jump? That's weird. Wait, did I? No, it is the implementation of a bad opcode, and we already reverse engineered it last time, right? And this is like incorrect password or something. So if we go here, where's the bad? Here's the bad thing. So okay, so we know this is like puts, probably it's like puts whatever, puts wrong pass, bro, like, yeah, whatever. Okay. Why would an offer of this double VM would make opcodes that predictable? Because why not? As in, it's a painful challenge in its own, and I do like to make fun challenges. I do not believe that fun challenges need to be super hard. So yeah, there could be like multiple things to be done here to make it harder, but like it's still like falls into reverse engineering 500 category. We are missing only a couple. Let's look what this lead thing is. Okay, lead thing is going to be on this address. And yeah, this is it here. Because this was the knob, right? So this was like, this is the knob. Yeah, there's a storm outside. Now my security mind is telling me that based on the timing of the thunder, if you could hear it, you could probably get my location pretty accurate. I wonder if you could actually do that. Okay, anyone surprised that lead means actually congratulations, the password is correct. I mean, I'm guessing. Let's actually look what do we have here. So let's do Python. Let's get it with like this. Now let's do it properly. this, and then this. Okay. Okay, let this be K. Oh wait, no, I don't need unpack, I need pack. So pack for I, because we need it to be switch little endian. And K. Well, great work. Okay. So yeah, we know that lead is just like puts great work. Yeah. Okay, so puts great work. 888. What is 88888? This is jumping here, which I guess is here. So no, this is 888. Okay, what's going on here? This is yeah, this is yeah. It's weird because this is like it's jumping sometimes to different addresses. One is jumping to somewhere at the where are you jumping anyway? There are a couple of opcodes which are jumping here, and there are a couple which are jumping here. It's pretty weird. I don't fully grasp the difference. Why is one set of opcodes jumping there and one somewhere else? Okay, so what's going on here? We read ECX is we store this value in ECX. Sorry, in EDX, and EDX being IP, right? No, not IP, it's the R7 thing. So this is like R7 is going to be equal to this ECX thingy, which is no, this is, wait, what is going on here? No, this is okay. What is this address then? Ida, could you tell me where this address is located? Sorry, go this address. Okay, hello there. What are you? That's pretty weird. Why do we find random bytes in memory suddenly? But on the other hand, these bytes don't look that random, right? They look a bit random. Like 8 is here, there's a lot of 8s, then there's 4. I'm not really sure what this is. No, wait, I have an idea. Okay. What are you? Why do these addresses... Oh, these are like some... These are the addresses of like... Okay. So if I store this under this address, which this address is the... It is the register, right? I got it right. Yes, this is the address, the register. And I store this like... Is there another VM in this? I don't understand the purpose of this code. I have no idea what this is. But I'm going to transcribe it to like this, and we put there this. Am I between two airports? Well, given that Earth is, you know, like a globe, I'm probably between all the airports in the world. Somewhere. Though... and there are actually enough airports in, like, in 50 kilometers radius, but I'm not sure if saying I'm between two airports is accurate either way. Cool. Yeah, I don't know what it does. And then it jumps somewhere here. Let's go there. It's probably going to be like this. Okay. So we jump here. And what am I looking at? What are you? Okay, that's pretty weird. I have no idea what this code does. Let's take a quick glance. This AT, that's the instruction pointer. So we grab the argument. So okay, we grab the argument. So EAX has the argument. Then we set ECX to 4. We multiply the argument by 4. So now like, and that's what goes into EAX. So EAX is multiplied by 4. Then we decrement this address from, so we increment basically, what's this value? This value I want to do minus on it. So minus OX, okay, and now I want to do truncate it to 32 bits. And I want to display it at hex. It's some address somewhere in memory. What kind of address are you? I don't know what memory range is this in at all. So okay, what we basically do, what's going on here, right, is that we are using this as a array of something where arg times 4 is the index. So this is doing something with that. Okay, and then we load EAX into EAX. So we grab this and we load it into EAX. So EAX is now equal to this array. Is this a password array? It's not the password array, is it? Not here. No, it's not the password array. It's just like middle of memory, I don't know. Some empty buffer which we can probably use. Then in EDX we put this 9C thingy, which is quite close to this. Is what, 16 bytes? A little further than that. (16B088). Oh, this is basically the register table. So these are the registers, like regs. So okay, we grab an, based on the argument, we grab a register. This is starting to make sense, and I like it. This is probably like, yeah, do something based on the register, like read a register, add 2 registers, or whatever, and the register is actually the argument. This is good. Then, from 9C, what was this 9C again? I don't know what was this 9C. We put this 9C in, 9C, BO9C. Okay. I'm starting to think that there are actually only 4 registers after all, and these are like temporary values which are used at the like internal registers of a VM. That's my current pet theory, or like a hypothesis, rather. We are going to check what are the arguments, basically, because this instruction will reveal how many registers are there, because we will be able to just disassemble this shortly, like these instructions shortly, and after we done that, we will be able to I think I know. No, this is PopAX. Yeah. I was looking like maybe this like puts the operation there, like for example, is it a addition or a subtraction? Whatever. So in this we put EAX in this. So we put the value of a register in this temporary register 7. not 7, 5. We are using R5 somewhere else, right? Like here. So like R5 is going to be like register regs based on this. So like so much code, right? And we basically reverse engineered this, but okay. Let's continue reading. Then we do read this value, which is before the instruction pointer, +4. So this is reading the instruction pointer. We subtract, we add 4 to the instruction pointer. So IP +4, and what do we do with it? And we put in this address, so in the instruction pointer. Okay, so we basically do IP +4. So that means we read the argument and we shifted the instruction pointer by the argument size, which is correct. That's easy. Then we grab the next argument. So okay, there are 2 arguments now. So we grab the next argument, and guess what we are doing? This is the same constant, right? Is it the same constant? Yeah, it is the same constant. So we are doing exactly the same thing, and we are putting the result in... Where are we putting the result? ECX, we minus it, then we put it in AO. R6. Okay. So we know that in R6 we have, after here, because this is the same pattern, right? So in R6 we have the second argument. So this is argument 2, this is argument 1. I will bet you now that we are going to find this, like IP +4 again here. So we go to, okay, here, let's continue reversing from here. We read IP, we increment by 4, we store it, as I said. So this is again IP +4. So we are reading 2 times, two arguments, and we are progressing. So if it would be like, I don't know, let's just grab this 888. Here, right? This is the opcode. And this is like argument 1, argument 2. Now, if we go to, we read the A4. We read R7 and we jump to R7. So this is jump to R7. To whatever is the value in R7. Is this correct? That's correct. And this is probably not returning. I wouldn't expect it to return. So yeah, this is basically helper code, which is used by multiple instructions to read 2 arguments. And 88888 is the first one of these instructions. And this is R4. Yeah, it is R4. Sorry, R7. So this is R7. And now we jump here. So we jumped. Then basically read 2 args, continue at this address. So now we go there. Oh, surprise, surprise, this is this. So we end up here. Okay, so we continue here, and what's going on here? It takes, let me guess, it's going to take both of these. Takes one, takes the second. Yeah, loads one to EAX, loads the second. Then it multiplies them, and then it stores the result in 88. 88 being R0. Perfect. This is, yeah, we figured out what's going on here. This is actually like, R0 is going to be equal to Rn multiplied by Rm. A lot of complicated code for something which we reverse engineer in the end to like this. Okay, that's fine. That's how reverse engineering works. Perfect. So now that we know this will simplify a lot the other stuff we are going to look at. let's go with are these going to be shifts, like shift left, shift right? Let's see. We need to jump here to analyze it. Yeah, it's going better and better. Okay, here. This is this, and hey, guess where are we going? We're going here. This is yeah, this is our code, which means I should note somewhere. But this is read to args to R5 and R6. Yeah. Therefore, if we continue, let's backtrack. And that's not how you backtrack, that's how you backtrack. Okay, so we read two arguments, and then we continue at this address being here. So read to args, continue at this. And here we are grabbing the first argument and the second argument probably. So this is like 98 plus 4, yeah. And we are XORing, this is XOR. Okay, perfect. So we now know that this is R0. Are we writing it back to R0? It's 88 where we store it. 88 being R0, yeah. So this is R0 is Rn, XORed with Rm. Perfect, now let's look at this. That was easy. Here we go to here. This is going to be this opcode, and we are using again this address. Yes, we are using this address, so we are continuing then here. So it's again using it's OR. Yeah. Like, we know the pattern, we've seen this pattern, we analyzed it, we just look for the key instruction, which is OR. It's OR. So these were not shifts, it's OR, just to double check. 88 for, yeah, it's 88, so it's Rn or Rm. Cool, cool, cool. Now we said that 0000 is weird, so let's go back to analyzing this 0000 thing, because if it was weird then, now we might be able to analyze it again. That's what I said, that it's not important to get it right at the beginning, because we will be revisiting it. And therefore we need to jump to this address here, which is 00. Yeah, and this is basically this is the same pattern, but this is a different jump. So we need to go here and analyze. My guess, so we know this is read two arguments. My guess, this is going to be one read one arg. Therefore, let's go to this address. Yeah, it's here. Now again, we know the patterns. This is read the first argument, grab the register table, and put the value from the register table to 9C, 9C being R5. Sorry. Okay, so here we know that R5 is going to have arg1. Then, sorry, this is actually like regs of arg1. I guess we call it like Rn. Like the value from Rn. Then what's going on here? Because this is a different pattern now. EAX is equal to 80 plus 4. No, this is the same pattern, but this is yeah, okay. So yeah, we are basically here we are incrementing like IP plus 4 plus equals 4, of course, and here we are getting the address back from this address where we stored it at R7, and we are jumping there. So yeah, this is just as I expected. This is redo. Wait. That's a mistake. It was supposed to be like this. No. I have no idea what this address is anymore, but whatever. Yeah, so we know this is read two arguments. We can go, so read one argument, so we can go back there. Let's go back there. here arc and jump back. So R7, I guess this is like a return register. Okay, so we read one argument and we put that one argument into R5. Now what is going to happen with R5? We are going to read an argument, so we read an argument. So here in EAX we have like the second argument, because the first one was the register, right? And then we are going to grab the A0 thingy, A0 being R6. Why is it grabbing R6? And we store in R6. Okay, so we store like R6, the temporary register arcs is R2. Then we get 80 plus 4. This is incrementing IP. So this is IP increment. Plus 4, and then we jump somewhere. We jump to this address. 702C. 702C here. So we jumped here. And now we know that we have like in R5 we have the register value. So it's like regs arg1, and then in R6 we have the argument 2. And what's going on here? We from 9C register 5 we are reading it to EAX. We are putting it in ESI. Then we are putting 0. From EAX we are subtracting 0, and we are checking if argument 9C argument, if this is 0. So if our like reg of is 0, then we oh, thank you for the donation. Terror Beats, thank you for the donation. Yes, we jump to these two addresses, which are important. One is going to be here, and the other one is going to be from B here. Somewhere here, yeah. What's going on here? This is like a super weird instructions. Okay, this is basically is this equal to 0? Then jump. Then we grab it from ESI. We still have the value in ESI, and we compare it with 1. And if it's 1, then jump. And then we compare it with 2, same pattern, with 2, you can see the 2 here, and jump. And depending on the value of this, we, where do we jump from here? 10. We jump into one of these cases. So it could be 0, 1, 2, or anything, and it will jump into one of these cases. Oh, this is storage. Yeah, okay, so perfect. We actually realized a couple of things. First, there are only 4 registers, because there are 4 cases here. These registers, they are not real registers, these are like temporary, virtual, hidden, internal registers, whatever you want to call them. And what we put in argument, and which argument? In this is C. In argument 5, yeah, so we don't grab the, I don't think we grab the register, we basically, or we might grab the register. And we will, no, but this is +4, okay. So yeah, we are going, this is basically like, we are going to take this value, which is in R5, and we're going to store it in the register, which is pointed to by R6. So this is like store in reg of R6, whatever is in R5. This is basically what it does. So now we know. Now we know, and this is going to be useful to know this. Let's go here. This is 2C actually. This is store R5 in regs R6. And yeah, and it will be like picking one argument by one. It's picking from reading from R5, and it's storing it into first register 88, second register 80C, 90, and third, and then it's jumping back to I believe it's jumping back to the beginning of a loop, right? Yeah, this is like jumping to the beginning of a loop. Perfect. So now let's look at let's go back actually. I think that's just a move. Like the whole instruction is just a move. Oh, I think wow, my history is so long. Did we just jump from here? Yeah, we just jumped from, now this is like, okay, here, perfect. Therefore, this is just a move. It looks complicated, but this is just a move. So it's like move, like, or whatever, Rn is, we are going to put Rm there. We grab one value and store it in the other. Yeah, we just have to figure out which is which. In R6 we put the argument 2, and this is where it's going to be stored. So this is yeah, like first arc1. No, this is like arc. How is it like this? M and okay. Cool. That actually clears up a lot of what I was looking at. Now let's look at this feed data thingy. Feed data. Oh, we have only a couple of instructions left, so I guess we can soonish we can wrap it up. I do expect it to, once we have this, I do expect it to be 10 minutes and we'll have it solved. That's my expectations, because there isn't a lot of opcodes and they seem to be really redundant. Cool. Now, this is here. So this is the feed data thingy. And what do we do in feed data? In feed data, we grab in EAX this value, which is R3. And we read from this thing, which is the pointer to the password. So this is reading data from the password. We grab 1 byte of the password, and we store it in R0. So here, R0 has a password, like the byte of the password. And let me guess, I'm going to tell you without looking at the code what's going to happen next. This pointer in R4 is going to be incremented by 1. So we read the value which is in R4. We put -1 and we subtract -1, so we add +1 and we store it back in 98 in an R4. So yeah, this point is just going to be incremented, which means this is basically like I guess like next of password. Let's call it like this. Like grab the next character of a password. So when we look at the feed data thingy, let's look at the feed data thingy. Let's look at the feed data thingy, but with reversing. It's here. So if feed the data, like we read it, then we do 666, so I have no idea what we're doing yet. and then we are like multiplying something, then 666 again, and then some other. Yeah, so there's going to be some easy math operations going on here. Since we know this already, you know what? A fast way to solve this, and if this would be a CTF, the fast way to solve it is I would place basically, I would just place breakpoints on the gadgets which are responsible for multiplication, for XOR, and for this to figure out what values are being used and be done with it. But since this is about analyzing virtual machines, we can continue. Now let's look at this. What is this going to do? This is just writing stuff to memory. I can tell you that already without even looking at the code, because the way of how it's used, like, yeah, like one argument, the argument being really weird high entropy string, this is pushing data on the stack. So if this is going to be the push, then we got 666 right on the head is going to be a pop. Okay, so given this, let's analyze it. I'm going to go to the end of solving this, by the way, today. This is like 777. We read the argument, so we get the argument into EAX, we get the argument. Then we get the 9C thingy and we store the argument. 9C thingy is R5. So in R5 we have the argument. Then in EAX we read, so we know this pattern, right? This is increasing IP by 4, so IP plus 4, we know this pattern already. Then if we look at this, we are getting A4 plus 4, so this is the thing which we call the stack pointer. It is actually a stack pointer. We are incrementing it by 4, so this is like stack pointer plus equals 4. So yeah, it's stack growing in the opposite direction when it's growing on x86. I guess my camera is reversed, so yeah, the stack is growing this direction when on x86 is going this direction. And then we store, so we store this, the stack pointer, then we grab R5 and we store R5 into whatever is the value in ECX. ECX being, that's weird. So we load the value from ECX to ECX. This being R5. Okay, so it just loads R5 and it stores it in EAX, EAX being the new stack pointer. This is push. So yeah, this is like push argument 1. Push arg1. We can analyze 666 now again, but it's going to be a pop, and we know it's going to be a pop. But let's analyze it anyway. It grabs the argument. 84, yeah, so it grabs the argument. So this in R6, yeah, this is R6, we get the argument. Then we put, and here, this jump here at the bottom, which I misinterpreted as going back to the loop, is store. So this is a typical pop. Yeah, so this is pop to Rn, where n is, based on the argument. We have now everything is now analyzed. We have nothing else to look at. What we need to do now is we need to basically disassemble the code, decompile the code. And to do that, I'm going to write a short, like this, to.py, a short Python script. And what's it called? It's called like dump1, the file where I have it. So open dump1 read binary as f d equals like f read. Now what I could use actually is like import. How do I import? I guess like from struct import everything. And now I can do unpack from EI and take data from D. Here what I want is length of D by 4. Okay, and let me run it. Python this too. Okay, yeah, this works fine. So I'm just getting everything as the words. So like, I don't know, like let's go to instructions. Now I equals 0 while, let's do it nasty, in a nasty way. While I is less than length of instructions. Now, okay, let's do it nice. Print hex ins, okay. Hex cannot be ins of I, obviously. And this is an infinite loop, my favorite kind of bug. Okay, it's going well. Now we need to basically let's just do print hex. No, this is not nice. How many of these do we have? I have no idea. Let's do 4x, then the instruction, which is going to be s, and yeah, alright, sounds good. So what I want is, I want I times 4, and I want like this assemble my instruction ends I. Okay, but actually when no, I need to disassemble it prior to this here, and I'm going to get like some string which explains everything, and then I'm going to get new I, and then so here I'm going to put the string, and I'm going to do I is new I, and that's perfect. Now this function is going to grab ins and I, as we know, and it's going to like the instruction itself, so like in a stable, I don't know, whatever, doesn't matter. Instruction itself is going to be, I'm sorry but I'm confusing the names. When we do and we return like some string, so like explanation is going to be this. So we return the new I and s in this order? No, in the opposite order. Okay. Now, if instruction is equal to this, you know what? I'm just going to copy it. I can just copy everything actually. Okay. Sorry. Okay, yeah. If ins is equal to ox this, then s is equal to this. Okay. So this is like the easy way out, but we know that there are some cases that there are 2 arguments. So this is where there are 2 arguments, we do I plus 2. We know there is 1 argument, we do I plus 1. We know there is 1 argument, I plus 1. No arguments, 2 arguments, 2 arguments, then 2 arguments, push 1 argument, pop 1 argument. Okay. So this is the easy and simple nasty way to do it. We have already some stuff annotated, but it's printing something which it shouldn't. So yeah, let's do this. Okay. Perfect. Now, now we need to actually get the arguments correct. So for the push, we get push and the data, we should collect the data by the way, but we are going to do it in a second. In mem I, yeah, okay, this is cool. Next password, Okay. Then here we actually need the registers, register numbers. Mem I plus 1. Here and here the same. Percentage I. I'm not sure if I'm getting actually the argument order correct, but as you can see, it doesn't matter in well, in none of these three instructions. Here I am go-toing somewhere. I'm really curious what is the convention of the go-to here. It should be like real addresses probably, and we will have to probably fix it in a second. So mem of I, this is fine. Here there's another go-to x mem of I. Here we have two arguments, which is argument 2, argument 1. So do mem I plus 1, mem of I. Okay. And it's just a move, so we can do like equal. Let's just use this arrow. Okay, so this is a little better. Now let's try to disassemble it again. Okay, and we have, yeah, this isn't out of code. We are pushing some stuff on the stack. Then we are doing pop red, and okay, this is one thing I forgot. Here. So pop and mem I. Okay, let's do it again. And let's like write it somewhere. I don't know, like layer 2.this. So we are pushing some stuff on the stack. Then we... Oh wait, I want to check the go-tos first. The go-tos are going to be incorrect. What is this value? This value is this, which means here I actually need this. This I don't need. I need this plus, okay. And this should actually show me, yeah, it should show me that if it's jumping here, it's actually jumping here. Perfect. Okay, so yeah, there's not a lot of code. First we initialize stuff, then we basically in R2 we put this value 1c, which probably 1c, my guess, 1c is the length of the password. Then we grab one character of the password, and the password is going to be put, it's probably put in R0. So this is put in R0. Then we grab the value from the stack. So here we grab this value, not the last one, this value actually. We multiply whatever the password is by this. Then we grab the next value, which is this. We do an XOR. And then we increment R0. We take R0 and we OR it with R3. And then we put, okay, so this is a constant time comparison. A constant time comparison is when you don't bail out early. Like when you know you are comparing two strings, and there's a difference. So you don't bail out early. You go to the end of a string, and then at the end of a string decide whether there was an error or no, and bail out then. This is typical way you do it in cryptography, and this is the way you do it if you do not want to like be vulnerable to side channel timing attacks, basically. So this is so R3 is basically, I guess R3 is 0 at the beginning, and here we are just doing a constant time comparison of R0 and R1. So yeah, this is the value. Okay, perfect. Then what's going on then? Then we put R2. What is R2? Oh, this value. So this is, yeah, we are decrementing it and we are storing it. So okay. So we are doing this. Then if it's 0, then we go to CC. When CC is here, otherwise we jump to 54, which is the beginning of this loop. So this is a for loop. Then and then if if R0 is equal to 0, then we set R1 to 1, and if it's 1, then we go to FC, FC being here. Yeah, this is super easy code. Like, what we need to do is we need to basically reverse engineer these values, I would say. We grab this value, I'm looking at the values, okay. So we grab the value, we multiply a character by them, and we try to get this value. This is what we are trying to do. Otherwise, we can grab this value and I guess like divide by this value, and we should probably get a character. We know the flag format, by the way. The flag format is GR, yeah, like this. So we know that if we get the algorithm correctly, this should basically give us the D letter. Which means, let's go to Python. Now, we grab this value, which is the result. We divide it by this value, which is being actually, you know, multiplied by, and we get some weird large number, which I don't like. Wait, did I do the correct thing? We grabbed the password to R0, we multiplied it, we grabbed the next number, and we compared it. Then we increased R0 by 1. Oh, we increased R0 by 1. So, wait. That means that this is wrong. This means it was, should be like this. Minus 96. 60. Okay. That's better. CHR. I'm not really sure about that. Well, there are two ways to approach this problem. One way to approach this problem is to try to figure out and reverse it. The other way is obviously to brute force it. And when you're tired on a CTF, you're going for the brute force approach, which I guess what I'm going to do. Basically, I'm going to do like A, B, and the function is going to be called X. We are going to grab, yeah, A, B, which is this. Then what we are going to do is we're going to do basically R0 is okay. So R0 is the CH, and we do CH is equal to CH multiplied by A, then CH is equal to CH XORed by B. This is cool, but I'm actually operating in 32 bits, so I need to do an AND. Okay. Same. Well, this doesn't need it, but okay. And then we need to increase it, so CH plus 1. Plus 1. Okay. And then if it's 0, basically like return CH equals to 0. And now I'm going to like just loop through it. For I in X range. I know that this has to be printable, right? So I'm going to do this. And I want if X of, maybe I mixed the values. I think this one is going to be popped. Well, whatever, doesn't matter. So this is the first value. This is the second value. And my CH is I. Okay, print CI, there. D. Okay, yeah, brute force always works. So, to wrap it up, what we need to do is we need to basically grab all these values here. We need to grab them, we need to put them here. Here, okay. Let's grab them again. Let's do OX, let's do this, and let's call them like constants, like CS. Okay, and now we need to iterate through them. So basically for AB, and how do I get to them? I need to zip like CS from 0 by 2 and CS from 1 by 2. Okay. And for each constant, and I basically also need to go from behind. AB, okay, then O equals plus, wait, wrong. O is the output, and we print the output at the end. And obviously it didn't work, because why would it work? Okay, so we start with these two values, but did I mix up the order? I mixed up the order, I think. Yep. That's it, we got a flag. The RGNS, what the heck was that? That is exactly my question, so I guess we spent 4 hours basically reverse engineering it, and in the end we used a brute force to go about it. But yeah, basically that's it. Basically that's how you can approach solving a VM. Important things to take from this is that you will need to write your custom disassembler, and you will need to understand the bytecode of the VMs. If the VM would be more complicated, I would like improve my disassembler. Would probably like introduce labels instead of these, like whatever kind of labels. I might want to write code which looks like C or C++ or whatever, and then compile it and put it in a decompiler. So there are a lot of ways to go around it, but go about it. But that's basically how we approach it. And I think how fast was that brute force? Well, as you can see, it was like instant. It's instant because there are like 30 characters, and there's like 96 times 30. That's nothing. That doesn't even register. Super small. I guess like it's a good thing to learn, especially for CTFs, but also for security in general, is being able to quickly estimate how long will a brute force take. Here, I just I looked at it and I knew it will be super quick. In other cases, I might do some math actually to figure out, hey, is this going to take an hour or is it going to take 1 week? So yeah, estimating brute force is also important. So that's basically it. Thank you for sticking with me. I see there are actually more people now than there were in the middle of the stream. I'm going to upload all the tools and everything else to my GitHub. And thank you, Pavel, for the donation. Yeah, Dragon Sector, awesome. I totally agree. So thank you again. And that's a nice round number, 2 to the power of 5. Perfect. So that's it for today, unless you have questions. Let's look at questions. The questions will appear here. Kitty asks, when ray tracing, when OSDev? These are topics for the Polish live stream, so I'm not sure why you're asking about them on English live streams, but okay. When the next book, after I publish my first book in English, because I still didn't, as you know. When next blog post? Hopefully soon. When Foxtrot Charlie will receive paycheck from you? Paycheck. I don't know. I mean, he's a volunteer, right? And actually, you know, like business between me and Foxtrot is classified. I'm sorry. Foxtrot says that there is no need for that. Kitty, when something about FreeBSD today is FreeBSD Day. Happy FreeBSD Day to every FreeBSD fan. I don't know. We might someday. How's the second VM on performance? So it's the second VM is obviously like slow. It's not great. It's slow, but it's a typical VM performance. It's not super slow. Actually, the turn-oriented programming chain is going to be slow, but not for the reasons you think. It's going to be slow because it breaks a lot of like prefetching mechanisms, basically, and like on the CPU cache, especially instruction cache. So it might be slow due to these reasons, but apart from that, it's not super slow. It shouldn't be super slow. And the complexity isn't... Well, the complexity is, as you say, basically like n squared due to like, yeah, but you have basically a loop for each VM. Well, not really. Because the first one isn't a VM, it's a weird machine. So no, the complexity should be like normal O of n, where n is the number of instructions, or no, that will be squared, because that's like the numbers of instructions is one thing, but the number of opcodes is the other, because we are not doing any smart jumping to like whatever switch case block. We are doing one by one comparison with a if list, basically, so it's going to be slow. But yeah, not super slow. Do you have to learn a certain programming language in order to reverse engineering? No. It's helpful to know the basics, but basics are enough, basically. The deeper you go into analysis of the application itself, the more useful it is to know the language and the frameworks and the libraries and everything else. But before you go there, then no, just the basics. And not even the basics sometimes. You will have to learn a lot on the way, though. I'm new in cybersecurity, and I was wondering what's the best way to learn how to reverse engineer? By doing it, basically. That's like... So, I guess like the... Oh, wait. I actually written a blog post about it. Now I remember. And I written it especially to answer questions like this. So if I have my browser, I find my browser. Hello, my browser. If you go to my blog, which is genvail.coldwin.pl, and you go to the English site, look for FAQ, and yeah. The first one is how to learn reverse engineering. Take a look there. Like every tip I know I've written here, and there are some both exercises and some links and like some other stuff. So like also a quick introduction to what methods are there. Do take a look at that. I totally cannot tell you more than I've written here about how to start. So yeah, thank you for asking. That's always a chance for me to basically show that blog post. There's another one about vulnerability research, basically. Totally out of subject, but what do you about Go? Is it good for security? Yeah, basically Go, like Rust, is a language which doesn't have memory corruption bugs by itself unless you're starting to use unsafe modules. Then yeah, so in that case it's a step in the right direction from C and C++. When it comes to security, I'm not sure about everything about Go. Is everything defined, for example? But it's a nice step, like from C, when it like still system level language, right? But it's a nice step when it comes to not having memory corruption bugs. But yeah, I guess like Rust or Java, you can say the same things about them. Like there are no memory corruption bugs in Java or in Python, right? And I guess that's it for today. So thank you very much for everyone for being here, for sticking with me until we reach the end of the challenge. Again, that was like 500-point challenge from one of the Dragon Sector CTFs. And I guess that's it. Again, next week, no stream. In 2 weeks, probably no stream either. But we see each other, I guess, on the Google CTF in a couple of days. So thank you to Foxtrot Charlie and also KrzaQ for being my moderators today. And I'm going to leave you with some music, and I wish you all a happy day, a happy evening, and have fun with, hacking, reverse engineering, programming, whatever you do. So that's it. See you next time.